A very good evening to all the dignitaries. With the blessings of our Honorable Founder President, Dr. Ashok K. Chauhan sir, Amity Institute of Applied Sciences is organizing online guest lecture on an introduction to water waves and distribution of wave heights, which is related to ocean engineering and naval sciences by eminent researcher, Professor Dr. Trilochan Sahu sir. He is senior professor at IIT Kharagpur. A warm welcome to our respected director, Dr. Bikash Mishra sir, our respected HOI, Dr. Joyita Chattopadhyay ma'am, our respected HOD, Dr. Biplab Bagh sir, all respected HOIs and respected HODs, my esteemed colleagues and dear students. I request our respected director sir, Dr. Bikash Mishra sir, to address the audience. Sir, please.
Thank you, ma'am. Thank you, ma'am. I hope I am audible.
Yes, sir.
Okay. Yeah. Good afternoon to one and all. It is my privilege and honor to welcome you all for the today's expert lecture session of Dr. Sahu. I am extremely thankful to the today's keynote speaker, Dr. Sahu from IIT Kharagpur. I am really thankful and I welcome on behalf of Amity University to you, sir. We are grateful that you have taken out time from your very busy and schedule. I'm very much sure that today's talk is going to be very useful and very informative for all the researchers, for all the audience. My advice to all the participants who have joined this webinar is to make effective and best use of today's session. And I'm very much hopeful that by the end of the session, you will be having a great knowledge for the topic which sir is going to discuss. I once again welcome on behalf of Amity University, sir, and we are grateful that you have taken out time today to address our participants. Thank you very much, sir.
Thank you, sir. On behalf of the Department of Mathematics, I take this opportunity to invite our guest speaker, Dr. Trilochan Sahu sir, Senior Professor at Department of Oceanography and Naval Architecture, IIT Kharagpur. He has a research career of more than 30 years. He has been awarded his PhD from Indian Institute of Science, Bangalore, and completed his postdoctoral studies from the University of Hong Kong. He joined IIT Kharagpur in the year 2000. His research interest includes coastal hydrodynamics, wave structure interaction, hydroelasticity, etc. He has visited many countries like Hong Kong, France, China, USA, Japan, Korea, UK, Switzerland, and Australia for research collaboration work and for delivering invited lectures. He has completed 10 research and consultancy projects from various government-funded agencies of approximately 15.53 crores. He has guided 20 PhD scholars and postdoctoral fellows. He has more than 200 articles published in international journals of repute with very high impact factor, and also authored one research monograph. He is the associate editor and editorial board member of many international journals of repute. He is featured among the top 2% of global scientists for the last 2 consecutive years on Stanford University's list. He has also contributed towards various administrative activities of IIT Kharagpur. We now invite you to deliver your lecture and enlighten us with your words of wisdom. Over to you, sir.
Is my screen visible now?
Yes, sir. Yes.
Okay. So thank you, Dr. Smita Patti, for your kind introduction and inviting me to the Summit University of this Institute of Applied Sciences at MIT University. And I thank Dr. Misra, Vikas Misra, the director of the Institute, for his warm welcome and all arrangement which has been done, the administrative arrangement to organize this lecture. I thank all of you for organizing this lecture. And with this, I'll start my lecture. Today's lecture is an introduction to water waves and distribution of wave height. Since I was told that the students, basically it is undergraduate students, I will try to make a major part of this talk as very introductory in nature and informative in nature. So with this, the outlines of my talk will be, first I will introduce you to the world's ocean system and give a brief introduction to water waves, including the classification of wave theory. And then which is 15-20 minutes, in the last 15-20 minutes I'll spend on talking about the irregular waves followed by wave height distribution. These are some of the books. One book I follow this for this kind of things. If somebody want to know, and there is a series of lectures in one of the NPTEL course which I offered on marine hydrodynamics, where some of the lectures can be found, details can be found here. So now coming back to the general information about the world ocean, we all know that 71% of the Earth's surface is covered by ocean, and our major oceans, they was particularly the Pacific Ocean, 46%. It covered the space, and then Atlantic 23%, Indian Ocean 20%, and remaining contribute to 11%. And as you know, that average depth of the ocean is 3,800 meter, and the maximum depth of ocean depth is Mariana Trench in Pacific, that is 11,524 meters. That is the depth. And some of the facts about the Indian Ocean, its deepest point is Diamantina, deep in Diamantina Trench, which is around 8,047 meter deep. And next being Sundar Trench, which is 7,258 to 7,725 meter deep. This is just a brief about the world ocean system. Now coming back to some of the features of the ocean floor, we have continental shelf, then we have continental slope, we have continental rise, the abyssal plain, then oceanic trenches are there, volcanic island, then mid-ocean ridges. And in fact, you will another information is that Mauna Kea is the tallest mountain in the world and is located in Hawaii, and it only stands 13,796 feet above the sea level, and but the mountain extends to about 19,700 feet below the Pacific Ocean. So that puts the total height of Mauna Kea to 33,500 feet, nearly a mile taller than the Everest. So now coming back to introduction to waves and then the water waves. So when I say waves, and I say wave, like we say, sometimes we say zero. How to define zero? In the same way, even if today zero is not properly defined, there are a lot of hypotheses on which the whole concept is based. Similarly, waves also is a kind of hypothesis and on which everything is based. So it's a periodic disturbance which travels through a medium from one point in space to another point. And when I say wave motion, it means propagation of waves through a medium. Wave motion appears in almost all branches of physics. And some of the basic characteristics of waves are energy is transferred from one place to another in a wave motion. And motion of the medium is usually periodically oscillatory. Only the shape or form of the wave travels, the medium does not travel in general. So now coming back to a regular wave profile in one dimension. You can say that this is the picture shows that regular wave profiles of the basic things as what we call the peak, what is the crest, or the trough, which is at the bottom. You can see the lowest of the wave profile is the trough, what we call, and then you have something called wavelength lambda, You have amplitude, wavelength, frequency, wave height, and all these parameters, which altogether define the wave. And it's a one-dimensional wave. Eta xt is a cos kx minus omega t plus epsilon. K is the wave number, omega is the frequency, and epsilon is the phase. In fact, it's a one-dimensional wave, regular one-dimensional sinusoidal wave. You can call it as a, instead of a cos, you can take it as a sine. The waveform will change. It will be 190 degree out of phase. Now coming back to superposition of regular waves, suppose I have one wave with frequency omega 1, h1 is the wave height, omega 1 is the frequency. Similarly, omega 2 h2 is another wave, omega 3 h3 is another, and then 4 waves. If these 4 waves superpose, then this will give a very irregular pattern. But this, all these 4 waves are very regular in nature. So when you look at the ocean surface, which looks very rough, actually this is the combination of infinitely many such regular waves. When 4 waves shows such a irregular pattern, when you have infinitely many such waves, the irregularity sea surface looks like this. So this is a combination of infinitely many such waves. Now coming back to some of the activities related to ocean waves. Those ocean waves are very important when you look at in ocean engineering activity like ship, waterman transport, offshore structures, fixed and floating platforms, Navy, military activities, amphibious operations, coastal engineering activity, harbor, ports, dredging coastal structures, beach erosion, sediment transport. When you look at oceanography, you have the ocean environment, atmosphere, fishing, oil spilling, mixing pollutant transport. In the context of environmental engineering, capping contaminated dredged material, diffusion and dispersion of toxic material in ocean and coastal water, like many other things are there, but these are some of the activities of ocean waves. So now let's look at some of the types of ocean waves. You can see that very nice pictures of waves, and then all are looking quite different. And then see another one, different types of another type of waves. How the wave height is. It can be very, looks very dangerous sometimes. And the right side, this is this one is like a tsunami during storm, how the waves form. And then dead water, it's a kind of like a ship is moving and you have a fresh water on the top of the saline water, and you can see the ship, how much resistance the ship is facing because of the internal waves. That means here you can see the amplitude of the internal wave is much higher than the amplitude of surface wave. And that leads to the ship's face double resistance. One is because of the surface wave, one is because of the. Similarly, you can see a submarine, how the waves are affecting the motion of the submarine. So now coming back to waves in the sea caused by wind, that is the wind waves, and wave height, it depends on wind speed, distance over which the wind blows, and length of time the wind blows. Basically, now coming back to another type of wave, what we call the rogue waves, free waves that come out of nowhere, and it's created by the constructive interference of waves and current, basically for interaction of wind waves and surface current. And this kind of rogue waves, they're very common in southeastern tip of Africa. And you can see that how from the picture you can see that because of the wave current interaction, suddenly there's amplitude, high amplitude, the wave amplitude becomes very high, and in the process a ship which was moving in normal regular waves, it started sinking and finally sank. So this was due to Antarctic storm, the movement of the waves. So now coming back to free waves, you can say a wave that is formed by a disturbing force such as a storm, and it continued to move without additional wind energy. On the other hand, when you have a forced wave that is maintained by its disturbing course, basically one of the example is the tides. And now some of the users of this information of wave climate, like we say the Coast Guard, Navy, fishermen, every day we give the, in fact, in our younger days, these days also, always the news comes every day, like we have a weather forecast. Then similarly, the fishermen in the coastal area used to be giving the sea state, basically what is the kind of wave that is propagating, what is the amplitude, whether it is safe to enter to the sea or not. So that is so fishermen is very, very important for them to know about the wave condition in the sea, even if cargo ships are ship. Then we have the recreational facilities, then we have the research and academia, then port and harbor activities, and passenger ship, and then we have cruise ships. So everybody who are involved in these activities, they need to know the wave climate in the ocean. And coming back to the ocean waves, depending on the type of how we define the type of wave, it depends on the mechanism. and the period of the waves and the activities. Let's say see sound waves, sound that propagate in the water, that is basically what we call this as marine acoustics. It's a physical mechanism, it's compressibility of the fluid, and then it is very activity, this region of activity is interior of the ocean. Similarly, you look at capillary waves, basically it is due to the surface tension, and that is of the period is of 10 to -1 second. Air it is propagates at the air water interface. Similarly, ripples and wind waves, tsunami. You can see in case of tsunami, the gravity here you can see that as you go down, the period of the waves is increasing. Initially, we see in case of sound, the wave period is 10 to -2 to 10 to -5, whereas in case of planetary wave, the order of the planetary wave is in days. So when I say in days, it is you have to convert it to second to get exactly the period. So, or in hours. So if I say 1 hour, it's 3600 second, and if I say 1 day, it is 3600 1 hour into 12, 24. 24 into 1 hour. 1 hour is 3600 second, then into 24. That is the time period. Similarly, number of days, that will more. So that way the time period is defined. And this time period, based on this, the restoring force. What are the restoring force? So gravity is one of the restoring force. Basically, force necessary to restore the water surface to flatness after a wave has formed. And there are two types of wave. One is the capillary waves, and where the wavelength is less than 1.73 centimeter. You can think of that is the smallest possible wave that is propagated in the ocean, which wavelength is 1.73 centimeter. And whereas the gravity waves, its wavelength is greater than 1.73. It can be in kilometer, hundreds of kilometers, like tidal wave, tsunami, it can be hundreds of kilometers. So you can see, and then here you see in the picture, there is initially plane propagating wave capillary waves, and its wavelength is very small. Then you have the gravity waves, the wavelength starting from 1.74 onwards, and it can go in meters or kilometer also. But here you can see that the stiffness, there is a, if I say that when the wave height increases, does it increase and goes to infinity? No, it does not increase. When the wave height by the wavelength ratio is greater than 1/7, then stiffness, and this, if it is greater than 1/7, then wave will break. You can see at the extreme end, the waves, how the waves are breaking. So wave breaking can take place because wave cannot, the wave height cannot goes to infinity. So now coming back to ideal spectrum of wave, how the wave height is depending on the period. As I say that here I have taken the period from 0 to 24 hours. The waves, that is capillary gravity waves, which is in 0.1 second, whereas in case of wind waves, basically it is in a few seconds, up to 30 seconds. You have sea chase, which is 30 to 5 minutes. Then you have tsunami, which is of the range of 5 minutes to couple of hours, and then you have the tidal waves, it's 12 hours to 24 hours, and then planetary waves will come. But you look at the wave height of these waves, you can see that it is 10 to the 4 in centimeter. Then you can see beneath the tidal wave, which wavelength is the largest, period is very large, but its height need not be that large. Rather, the swelling part is here, the wave height is very high compared to the wave period. Similarly, tsunami, here the wave period is much more than the wave height. So tsunami, normally during a swell, ocean swell, the wave height is much higher compared to that of a tsunami, where tsunami is more devastating. Here the wavelength is large. In that sense, now let's look at the variable bottom. When the bed topography changes, how the waves are. You can see a regular wave in the deep sea, and when it is propagating towards the shoreline, you can see there is a sharp, the crest is becoming more sharper, and finally it comes to a zone where what we call the breaking wave, or the sharp zone, where the wave breaking takes place. In fact, and as you go down, in fact, in the deep sea at below, it is very calm. But only when it comes towards the shoreline, the depth is decreasing, and there is a friction which takes place, and then in the, because of the, in the swash zone where the wave breaking is takes place, then the wave motion become turbulent. So that's why in the coastal area, the wave become more turbulent, and erosion takes place, soil erosion takes place. But if you look at the deep sea, nothing happened because waves are regular. And again, at the seabed, even in fact, when it is below this dotted line, there's no wave effect is felt. So now coming back to capillary gravity waves, the ripples are very small. It's, as I said, it is in centimeter. It's very small. The wavelengths are very small, but it has very important role in satellite image processing, data collection, intra-satellite data collection. So these are the ripples. And it's coming back to wind waves and swell. Here we have the surface waves. It is influenced by the wind in a generating area. And what we call the swell, it's the waves which moved away from the generating area and no longer influenced by the wind. Then we have forced factors that affect the wind wave, that is basically wind strength, the direction for which the wind blows, and the phase, that is the uninterrupted distance the wind blows. Now coming back to winds winds are the most important factor for the waves. As the figure conveys, you can see the increasing wave intensity as the wind blows. And here wind speed, wind direction, and phase, they are the various characteristics which is defined by this. Now coming back to tsunami, another type of wave, what we call the tsunami, it's a kind of it's a wave trend, or you have heard this term tsunami. It's basically it's a wave trend or a series of waves generated in a body of water by an impulsive disturbance which vertically displaces the water column. What exactly happened? What is exactly tsunami? Su means harbor, nami means waves. It's a Japanese word in which basically Japanese coast is more affected by the earthquake. So that's why they are island countries. So they define this. Su means harbor and nami means, because their harbors are many times activities are interrupted, disrupted rather. So they call it as this is tsunamis comes from there. But the earthquakes, and not only the earthquake is only responsible, upon the landslides, volcanic eruptions, explosion, and even the impact of cosmic bodies such as landslide, it can generate the tsunami. You can see the devastating effect of. In fact, this is a picture which has been taken in the 2011 tsunami. And this is the tsunami generation, but basically in the case of an earthquake, you can see the tectonic plate movement take place at the bottom, obviously, and that will a lot of force will come, and that force will propagate because of the extreme high forces that will pushes the water body, and in the process the wave propagate, and it propagate in all the directions. On the other hand, you can see a tsunami. It's a submarine explosion which has taken place, volcanic explosion, and because of that the waves can be. The third picture here, you can see that due to landslides, submarine landslides, and then the last one is this is a bolide impact. That is what. Now coming back to here, you can see the earthquake motion, and it displaces ocean mass, and it generates the tsunami waves. And then on the right side, this is a picture of 2011 tsunami, where a file pool which was caught by tsunami, and you can see the large ships, which is maybe 300-400 meter length ships of maybe like a 10-story building. How they look like? They are just looking like a small matchbox, and they sometimes sink into the. Many ships were not able to traceable during the tsunami period. Many ships, they were like it fall in the file pool, and then it was missing. Rather, it was capsized. And in fact, here you can see a land side. You can see scientists working on West African, the Cape Verde Island, have found evidence that sudden collapse of volcano caused by a mega tsunami, which is around 73,000 years ago, and it created a wave which is a height of a 90-story building. So that is the kind of wave which the wave height is 90. It's if I say that 90-story, almost close to 1 kilometer, 900. At least if I say 10 feet, if I say 10 to 12 feet, then 900 feet is the total 300 meter, close to 300 meter wave height. So you can imagine the devastating effect. So wave generated due to tsunami and landslide. Here you can see that how the landslide is occurring, and that is in Lithuania, one of the example, and it has created a tsunami kind of situation. Here, this is another picture of the wave which has been formed during the 2011 tsunami in Japan. Now coming back to waves on the surface view of a wave, which is from the top view, and here you can see the density stratified. Basically, it's internal waves when you have two-layer fluid, and then you can see the surface view. And here you can see in a tank, you have a two-layer fluid, upper layer and lower density, and higher density, the lower layer fluid. And you can see the interface, the two, there is also a wave propagate. And on the surface, you will have a wave, and the interface also will have a wave. So there are two types of waves which propagate. Now coming back to another type of waves, which is during a storm surge, what we call the cyclone. We are very familiar because the east coast of India is most of the time prone to cyclone, whether it is Visakhapatnam, whether it is Odisha, whether it is West Bengal. We are very prone to cyclone, and every year recent quite few cyclones which has caused a devastating effect, starting from the 1999 super cyclone in Odisha. Then we have Aila, we have other typhoons, cyclones we have. So then you can see that how much the wave height can generate a simulated picture. You can see how the wave height is increasing during a tsunami. Here you can see this center, what will look like an eye, what we call the eye of the center. In fact, you will be astonished, surprised to know the eye of the cyclone is around 500 kilometers. And then you can see the area which will be devastating. It is hundreds of kilometers. When the storm is formed, hundreds of kilometers, it can affect the activities. But again, the direction in which, unlike a tsunami, where the wave can propagate in both all direction, in case of a storm or a cyclone, the wave, it will decide, the wind direction will decide which way the storm is going to be affecting. And then that is the wind, direction of wind is one more important factor. Here, what is happening? Tidal effect will be there, cyclonic effect, and then the wind effect. All these things together, it makes the cyclone more and more worse, and then in the process, devastation become more and more. You can see here one picture on the left side below that we have a 2 feet is the high tide during normal 2 feet normal tide, but during a storm, it has gone up to 17 feet. And 15 feet surge and 17 feet is the wave height. So you can see the devastating effect on the right side, how the building is, how the house is covered with water. Now here, this is another case of tidal waves. Basically waves and tides. When I say that tidal waves, it's basically tides are formed due to the gravitational attraction of water to sun and moon. And basically, it's basically the position of the more precisely, I'll say that Earth and Moon and the Earth and Sun rotate around common centers of, and this wave is the actual source of the tidal energy. So you can see during low tide, this area is dry, but when there will be high tide, this will be flooded with water. And some of the, if you sometimes visit Balasore or Digha, you'll see the impact of the high and low tide. Here I'll just give you a basic information on wave height information in different locations in India. If you look at Mumbai, in a particular day, it was taken, Mumbai tide, it was around 4.5 meter, whereas Port Dabhol, the tide was around 2.5 meter, whereas here we can see Dahej, in Dahej, it was around 10 meter wave height, whereas in Jamnagar, it was around 6 meter, the wave height was 6 meter, whereas Bhavnagar, it was around 10 meter, Gandhinagar, it was around 10 meter. So, whereas in the Andaman Island, Nicobar Island, it is the wave height is around 2 meter, and you can see in Visakhapatnam, it is 1.5 meter. So, this shows that at various parts, various coastal parts, looking at Andaman Island, here where the wave height is 2 meter, whereas you look at some of the ports, coastal area in Gujarat, where the wave height can go up to 10 meter. The height of the wave is 10 meter. So basically, it looks like a 10 meter means more than 30 feet. So like 3-story building. So now coming back to how we classify the waves. When we classify the waves, it is basically the wave height divided by the wavelength lambda. And there are two theories, one the linear theory, the other is the non-linear theory. When I say capital H by lambda is small, and then based on that, the linear theory is defined. And then the linear theory itself is defined what we call this as the small amplitude wave theory, where when H by lambda is high, we just classify them under finite amplitude wave theory. Under the assumption of a small amplitude wave theory, the waves are classified as a deep water, shallow water, or intermediate depth, depending on the wave water depth to wave length. That is, if it is greater than half, then we call it a deep water, and if it is intermediate depth or it's shallow water in a layman's language is different than what in technically, because when H is maybe the deepest in the ocean is 4 kilometer, average ocean depth is 4 kilometer, and a tsunami may be propagating whose wavelength is 300, 400 kilometer. But if you look at h by lambda, it will be automatically 4 kilometer by 320, suppose 320 kilometer, then it is around 1 by 80. So that way the tsunami waves are shallow water. Whereas in a pond, you may say the water is a deep water. So it depends on this factor is by lambda, how small or big that is based on that. Similarly, the waves are classified. These are Stokes wave theory or Stokes first order wave theory, small amplitude wave theory basically. On the other hand, when you look at the finite amplitude wave theory, there are 4 types of major waves which are called the Stokes wave or Conradal wave or solitary waves or Dirichlet function theory or Drukgyal wave theory. Now coming back to classification of wave, I have already defined whether the waves are classified as the deep, shallow, or intermediate depth, depending on whether h by lambda, basically water depth, that ratio, if it is less than 1 by 20, then it is shallow water. If it is more than half, it is deep water, and in between it's called. And then how the orbit of the water. In fact, if you look at the, you see the wave profile, but what happened to the how the particle, wave particle, how the water particle, the fluid particle, basically how they move. In fact, in deep water, they follow a circular path. Whereas in case of if in the vibration of the particle, when the particle vibration takes place, and if they follow a circular path, one cycle is complete before the second particle get excited. So if there is a complete cycle, no mass transfer takes place when there is no movement, closed orbit is formed when the wave is excited after one period. If there is no change in the position of the particle. But if there is a change in position when open orbit is formed after one period, if the particle does not come back to its main position, then there is a gap. Then we call this. This is the region where the mass transport will take place. So in only pure wave, there is no mass transport. But if there is a situation where the orbit is not closed, that means there is a mass transport. So normally you will see in a river, major mass transport takes place in the river. On the other hand, in ocean, you stand on the same place and you see the waves comes and goes, but same sand, same ocean everywhere you see. And if over years, if there is a change in shift in position, that is due to the mass transport that is occurring. But otherwise, in pure waves, you don't have any mass transport. Now coming back to deep and shallow water, in the particle motion is orbital, particularly elliptic path they follow in case of deep water, particularly when intermediate depth also. But in case of more circular, it will be in case of the water becomes more deeper. This will be more circular or more elliptic if it is shallow or intermediate depth. So this is the basic introduction about this. Now coming back to the wave theory, the simplest way we analyzed based on assuming the water is a constant depth, wave motion is in two-dimensional fluid, and then waves are of constant form. The water is considered incompressible. You ignore the effect of viscosity, any kind of turbulent motion, surface tension, etc. If you ignore this, we always look at the particle velocity. You represent in terms of a gradient of a function velocity potential phi, and in the process you will see that the governing equation will reduce to a Laplace equation. I think students are BSc, so they must be introduced to this partial differential equation. So the governing equation become a Laplace equation, and at seabed there is no penetration, so there will be normal velocity will be 0, so del phi by del y is 0, and in case of infinite depth, phi grad phi will tend to 0 as in case of infinite depth. This is the basic governing equation. This is the seabed condition, and then on the surface we have there are two conditions on the surface. One is that the pressure is assumed to be on the surface in normal weather. The pressure on the surface is assumed to be constant. So what we do, the hydrodynamic pressure, the fluid pressure at the surface, we equate it to the atmospheric pressure, and that is a constant, and we derive that we call the dynamic condition on the surface. Another condition comes here because of the air and water. These two, they are in diagonal. There is no gap between the air and water. If y is equal to eta is the surface, f is the free surface, then total derivative is 0, df by dt is 0, where d by dt is this. I think this is a little more detail. So, and then in fact, if you look at the Bernoulli's equation, you might have heard it in your secondary, but in differential form, the Bernoulli's equation is that this is a second order, it's a nonlinear equation, rather I'll say in that nonlinear partial differential equation, that is the pressure which you in our higher secondary also, you know, Bernoulli's equation, but in differential form, this looks like this. And then if you ignore the higher order terms, basically linear, make it linear, then your this quadratic term will go, and then del phi by del t is zeta, assuming the pressure on y is equal to 0, assuming the pressure is constant at the free surface. Similarly, we get a condition on the free surface in case of water that will be of this type. And then if you assume that motion is simple harmonic in nature, then this will reduce, this equation will be reduced to the first order condition. And then this is basically coming back, if I solve mathematically a problem, basically I have to solve a Laplace equation, which is the governing equation, subject to a free surface condition, del phi by del t plus zeta is 0. This is one boundary condition. You have a kinematic condition and you have a seabed. If these three conditions, I solve a Laplace equation subject to these three conditions, you will see that this eta you will get a sin kx minus omega t, you will be one of the solution. That means this will be a sinusoidal wave, plane progressive wave propagate at this sea surface that will be get here. This is the procedure, and those who are interested, they can derive this, how to solve this kind of equation, this kind of partial differential equation subject to the boundary condition. This is the detailed steps I have taken. I'm not going to that. And here you can see that my phi I have got. I assume that I have a waveform eta is a sin kx minus omega t. Then the corresponding velocity potential phi is this. This I have got after solution. This is the full solution. Now in this I have one thing I have you have noticed. Rather, I'll just come to this. Here, regular waves. In case of regular waves, as I said that the wave they are very regular in nature, and then this what I told that the regular waves are to call the Airy's wave or the Stokes first order wave theory. This was in fact started, the wave theory started by George Biddle Airy, and in fact the first wave theory was derived by him independently, assuming the small amplitude wave theory, what we call assuming eta is a small compared to the depth of water, and it was derived in 1845. On the other hand, 1847, what G.G. Stokes, Sir G.G. Stokes, the both are Knighthood fellows. So he derived at 1847, he derived the wave theory, basically the finite amplitude wave theory, of which the first order wave theory coincided with the Airy's wave. So these two people are very well known for the initial development of the water wave theory. Today, of course, after almost close to 200 years, the wave theory has made massive progress, and today we are looking at how to control the wave, how to control when a tsunami or a storm or cyclone approach, or how we can utilize even the ocean space and keep ourselves safe from this fury of nature, basically the ocean effect. So anyway, so these are the longer waves that travel faster than shorter waves. Small increase in time is associated with a large increase in wavelength. Long waves move fast and lose little energy. Short waves move slower and loses most of the energy before reaching a distant place. And here, this is basically, as I was telling, in case of deep water, this is a laboratory experiment, how the waves on the surface, you can see the particle, their circular motion, whereas at the seabed, after you go towards the bed, they move in the elliptic path. This is a laboratory generation of how the particle motion takes place. So this is a brief about the small amplitude wave theory. And there is, if you have the wave profile, you can get the wave velocity, wave celerity, wavelength, group velocity, then particle speed and acceleration, everything. And that will help us to calculate how the forces that are acting on the structure or particle motion and other things. So this is the way the wave theory is, simple wave theory comes up. Higher order wave theory comes because the first order wave theory is the linear wave theory, but it goes to higher order wave theory. Then they are rather more close to natural phenomena. Simple theory is the linear wave theory. In the higher order waves, they are more peaked at the crest, flatter at the trough, and distribution is skewed above seawater level. I'll just show you here. You can see a finite amplitude. Here it is not a very regular pattern. You can see it is skewed at the top and it is flatter at the bottom. So this is it's a kind of finite amplitude wave theory. In fact, 1802. In 1802, Gerstner was the first who developed this finite amplitude wave theory, and more than 200 years before. And then later, a cycloidal wave is limiting case of trapezoidal waves. And this theory first initially developed and what we call the Drukgyal wave theory. Rather, later the regular waves and other this finite amplitude waves in around 1847-45 it came. But later this theory have been again strengthened, like another theory what we call Panadal wave theory, and this again appear for 1/50. The when I say square lambda relative depth is 1/50 to 1/10, then the Carnot wave theory comes into picture. But another very important wave is the solitary waves. In fact, it was Russell who developed the solitary waves to kind of produce solitary waves. Once there is a small story behind it. Russell was just on the beach. He was riding a horse, and to follow the wave pattern, and it was looking like a large crocodile as if it's moving at high speed. But he observed that it's not a crocodile; it's something which is moving. And later he came to simulate it in the laboratory and developed the theory of solitary waves. And then this is the way solitary wave theory was developed. In fact, I will say that this is a Airy wave, very regular in Stokes wave. Again, it is a finite amplitude wave. Panadal wave more sharper at the crest and flatter at the bottom, and solitary waves. In fact, you have only a crest, you do not have a trough in case of solitary waves. Now, finite amplitude wave initially. In fact, this is the detail of the wave theory. Basic governing equation is the potential flow. Under potential flow, you have the Laplace equation, you have the kinematic and boundary, different boundary conditions, and then all this, then you must be aware of Taylor series expansion. If z is equal to h is bottom surface, z is equal to eta, assuming eta is small, you always expand it, and then you can, a lot of expansion is there. This is a perturbational approach again to from the general theory to get the first order, second order, third order wave theory, depending on basically the coefficient of eta. You substitute for eta, phi, and u in the original equations, and then collect the coefficient of epsilon, that will give the first order wave theory, collect the coefficient of epsilon square, that will give you second order wave theory, and so on. Higher order wave theories are developed based on this. And this epsilon is Ka, K is the wave number, is the amplitude of the wave. That is a very small number, is just under that the wave theory is defined. So this is again proportional approach for the first order, second order. This is the like this part, the free surface condition. This part, if I take it 0, this will give the first order, and epsilon square, the contribution part will be 0. That it gives me the second order wave theory, the surface condition for the second order, and so on. So this is what I exactly say, that the free surface boundary condition of the first order, for the second order and third order, and let's say a little more what I expect from an undergraduate student. But anyway, first order Stokes waves, this is the eta, this is the corresponding velocity potential. Then in case of second order, this is the form of the eta, and the corresponding phi is this. Similarly, in case of third order, a comparison of Stokes second order wave theory to that of first order wave theory, there's a deviation. There is certain deviation. So most simple is the first order wave theory, or as second order wave theory. If you take, then you get more accurate. Similarly, you have the other wave theories were based on the Russell parameter u, and these details I'm leaving it for time being. And this is a picture of region of validity of various wave theory. First order wave theory, Airy's wave. Then you have the second order wave theory. Then you have the Stokes third order wave theory and fourth order wave theory, and so on. So these are the shallow water region. This is the transitional intermediate depth, and this is deep water. You can see a variation between different wave theories. This has taken ages for understanding this. With this background, now with this background on waves and various wave theory, I'll just say what is irregular waves and how wave height distribution take place. I have more 15 minutes. Particularly, as I mentioned in the beginning, when I say that ocean waves, they are almost irregular and often directional, short-crested. Irregular waves can be viewed as the superposition of number of regular waves. And regular waves, they have the same frequency, wavelength, and amplitude. And sometimes we call them the monochromatic wave, which are regular waves of same frequency, only frequency is same, then they are called monochromatic waves. Unidirectional waves, some of the terminology, basically all the component wave, they move in the same direction. And in fact, most of the laboratory design waves are unidirectional, whereas multidirectional waves, basically if the wave components are in multiple directions, basically short-crested irregular waves. And another major example is the sea is always very rough and You don't know it's a multidirectional wave, does not move in any direction. Coming back to irregular waves, it is basically, as I mentioned, is the superposition of a number of regular waves. You have a irregular wave pattern is this left side. On the right side, first 4 waves are regular wave, where the combined effect is irregular waves, and this is the irregular waves. But then we come back to short crested wave and long crested wave. The crest width is very small in case of short crested wave, but the crest width is very large in case of long crested wave, particularly 2-dimensional waves are the crest appear very long in comparison to the wavelength, and these are short crested. Now coming back, I have talked about the dispersion relation. It's one of the relation which relates the in case of water wave based on the linear theory. We obtain this is the best dispersion relation. Omega square is GK tan hyperbolic H. K is the wave number, omega is the frequency. If you go to the dictionary meaning, the relation which relates the frequency with the wave number is called a dispersion relation. In fact, this is the dispersion relation. From this, if I say Kh is greater than pi, you will see that Kh is greater than pi, tan hyperbolic Kh will tend to 1, and in that case, that will be the case of omega square is GK, and that is the deep water waves. And particularly that what I was telling, h by lambda is greater than half. That is because his tan hyperbolic Kh is 10 to 1, and that will give you this. Similarly, in case of shallow water, Kh is less than pi by 10, which is equivalent to telling h by lambda is less than 1 by 20, and that is the shallow water. Whereas in case of intermediate depth, your Kh is less than pi by 10, less than Kh less than pi. So that is the case of intermediate depth. And here I have given 2 examples. These slides I'll be sharing. You can have a look at it. You can see from this slide here, one of the wave which 10-second period does a wavelength of 156 meter. But let's look at a wave whose where it is the water depth is 4 kilometer, and whereas the 20 minutes is the period. If 20 minutes is the period of the wave, in second you call it 20 into rather I will say this is 20 into 60, that will be 1200. And here I have taken the case of, you can see that how this wave can have the wavelength. Here I leave it to you to calculate. See that it is the wavelength when the depth is 4 kilometer, the corresponding lambda is 1200 into square root of 9.82 to 4000. 4000 to 9.8, I will call it around 200. If I take it 200, 12 into 2, 240 kilometer. If a tsunami which is propagating with a period of 20 minutes, it's the wave that will be generating has a wavelength of 240 kilometer. Imagine. So similarly, you can think of a case of a tidal wave where the wavelength is more than 20 minutes. Now, anyway, these are summarizing some of the things. My time is short. I leave it. How you solve this? Because as there are students of BSc, here I just take omega square is GK tan. This is a transcendental equation. If I have to get K, what is my wave number? I know the water depth. I know the period of the wave. Is it not a transcendental equation? You apply your Newton-Raphson method to solve it, or fixed point iterative method to solve it. This is what I say here. How the utility of what you are studying in your numerical analysis or a differential equations. And now coming back from a 1-dimensional wave to a 2-dimensional wave, it's, I call it in the K bar dot X bar. Here K and X are vectors, and in that case it's the wave propagating in the 2 direction along the X and Z direction. Y direction is the vertically downward direction along the water depth, and in that case, if you have X is a vector, it has 2 components X and Z. K is a vector, the wave number vector, it has 2 components Kx, Kz, and in that process, it will be a 2-dimensional wave. Whereas 1-dimensional wave, if you say theta is equal to 0, then cos theta will be 1 here, sin theta will be 0 here, so Kx will become K, and this will be 0, so that will be reduced to this, which is a 1-dimensional. Just I said one example here, when there are 2 waves, which there is a phase lag, phase difference between the 2 waves, epsilon 1, the other one is epsilon 2. What will happen when epsilon 1 is epsilon 2? Then this total wave will be 2 times of the same wave. But what will happen when epsilon 1 is equal to epsilon 2 is epsilon 1 plus pi, then you have eta xt is 0. Here it says that when waves are of same phase, the amplitude increases and it becomes twice. But if the waves are of different phase, basically 180-degree outer phase, you can see that will be the effect of wave will be 0. Combined effect of the 2 waves will be 0. So in fact, in any engineering practice, always where suppose I have wave is approaching towards me, I should have a mechanism how to create a wave which is 180-degree out of phase. So I'll nullify the effect of the incoming wave. So that is what, if I want to increase the wave, I create a wave which is again equal to similar of same phase. I create a wave and superpose the two waves. This is anyway. These are some few more questions. I leave it at undergraduate level. So I hope this can be answered by our students. In the regular wave, what is the energy associated wave energy per unit horizontal surface area is G bar is rho G A omega A is the amplitude of the wave. So this will be the, and then wave energy flux for unit wave crest is this given by this is d omega by d, basically it's a group velocity, that is the rate at which the wave propagate, and energy propagate, this is the rate now. And then in deep water this is theta C by 2, and whereas in shallow water Cg becomes C. So now coming back to wave spectra. In fact, we have understood regular wave, irregular wave. In case of irregular wave, if I say amplitude on one axis and the frequency on the other axis, what I get it? If it is continuously, wave frequency is changing continuously, then I get a continuous spectra. And if the frequency is changing point wise, every point, every time period I have a corresponding wave height, then I call this as a discrete spectra, and then otherwise I call it as a continuous spectra. Similarly, we call it a continuous amplitude spectra or a discrete. But in case of instead of amplitude, if my energy is given, if the energy is given, then for each time period, if I know how much energy is propagating, which I have given you the expression for energy. In fact, either I have been given either amplitude is given or energy is given. Many times satellite data gives us the energy. So in that case, since rho is constant, G is constant, basically A omega square is given to us. Either A is given or A omega square. If A omega square is given, then I can say that energy is given and otherwise amplitude is given. So that way the energy and amplitude spectra is defined. Depending on whether the data is discrete or continuous, then we define them as a discrete continuous spectra. Now coming back to the general form. C-state, as I mentioned, the C-state is a combination of superposition of many irregular waves. So this is the general pattern. I was talking about a single wave of this form, and if you have many such waves, you combine them, and this gives you the C-state. And in fact, if observer is sit at x is equal to 0, then this reduces to, and epsilon the phase is 0, then this becomes the simple cosine wave. And then C-state, in fact, in x, t, x, and t at any point in space and any point in at any point of time, this is in xt. But if you say that observer is only at a single location, then you can call it x is 0, and then it can be represented in this. So in fact, if I just take this, the phase I take into account, then assuming the observer is at a point x is equal to 0, then my eta can be written in this form, which can be written also in a form of this. And this is nothing but your cosine series, Fourier series. And this Fourier series can, in compact form, can be written as this one, in terms of a cosine series introducing epsilon, which is called the phase. And if I say that it's a periodic wave, omega is 2 pi by t, and then it's pi by p, its period, wave period is t, then an can be, you can get in terms of an, bn, and epsilon and the phase you can get. So then Fourier coefficient from Fourier series, if you are familiar with Fourier series, then you get the Fourier coefficient, this individual amplitude of the individual wave a and bn, or in together you can get this a, capital A. So that is the way we obtain. If the C-state is given to us, we know the surface profile. We can get the individual waves A and Bn. Once we know A and Bn, we can say that each of the waves we know. So that is the way. Only thing we need to know what is the period of the wave and what is the C-state. Then you can always get what is your individual waves. And then the energy, average energy per cycle, you can always get it. And the definition is rho g by 2 is just an integral d to d plus p over one period. Take the average of that, and then eta square t dt, and that will be, if you sum up this, integrate this, and then you will substitute for eta and integrate it, you will see this is just a summation. In fact, in mathematics, this is called, sometimes we call this as the Parseval's theorem. And then similarly, from this is for the discrete spectrum here, the wave, each individual data, the frequency omega n is known, and for each time period, and an is the corresponding amplitude. But what will happen if this becomes a continuous spectrum? If the data is continuously spreading, the frequency changing continuously, wave frequency changing continuously, then the C-state can be represented in terms of a Fourier integral. And that Fourier integral, that is the corresponding energy is given this. So this is the corresponding energy. And then we can say that S omega is the spectral energy. And autocorrelation method and the fast Fourier transform method, they are used to calculate the energy spectrum from the recorded wave. This is the brief introduction to how the C state can be represented either in terms of a Fourier series, if it is a continuous discrete data, and it can be represented as a Fourier transform in terms of Fourier transform if it is C state is described as a continuous spectrum. Then we come back to the case of directional. As I said, that unidirectional wave where theta is the angle is not changing, it is propagating in one direction, and theta is fixed. But if the angle is changing any direction, the wave is coming, then how we represent the C state? In fact, then this theta is entered. We introduce the theta here, and in the process, the C state is defined in terms of a directional spectrum. And correspondingly, now coming back, we have so many wave height. For a designer, what kind of wave height you will take? He will require one wave height. Then in that case, the C state can be, we have to define some of the wave height which are called the significant wave height. It's the highest 1/3, average of the highest 1/3 waves. Then we have the HRMS, root mean square wave. If I have n such wave, then I take the HRMS I defined in this way. And then similarly, maximum wave height, this is also defined. Then in this, so we go to narrow banded spectra. And particularly if wave, all the wave frequencies, they are just around the particular frequency omega, then we represented in this form, and then we call this narrow banded spectra. Similarly, we have the another concept is here is the Rayleigh distribution. The C state often is represented in the narrow banded spectra, and in that case, what is the probability of wave height h greater than or equal to an arbitrary wave height? That is called the Rayleigh distribution, and from there, probability of h greater than h, this was defined in this way. And then the H naught, and particularly how we get the at an arbitrary any point. This is a kind of probabilistic approach to define, unlike a statistical distribution. Here we have a probability distribution of defining wave height. Then HRMS, these are some of the HP, and in HRMS there are some relations. This is a probabilistic approach. And then probability density function was a distribution probability, Rayleigh probability distribution function was defined in this way. From there, we can also relate the individual weight. So for a designer particularly, you have so many wave height. Which wave height you have to follow the probabilistic approach, or you have to follow the statistical approach, or you have to go for some of the Rayleigh distribution approach. Some spectral methods are also discussed, and I will not go to those things in detail. But here my objective was to introduce various concepts, how the modeling concept from starting from basic understanding of what is ocean wave and how to, there are theoretical approach, there are numerical approaches, and then finally probability and statistical approaches are there to define the C state and the distribution of wave height. With this, I'll conclude my talk. It was a very compressed talk, and I hope I have tried to explain some of the things to you. Thank you all. I will be very happy to, if you have any question, to clarify.
Thank you, sir, for this wonderful session. For any question, please write in the chat box. I have one question, sir.
Sure.
Airy waves, you told these are linear waves, right?
Yes, yes.
And
yes.
what about the tsunami waves? Are they irregular waves?
No, it can be, it is represented, but in case of tsunami, I told you, I have few things I'll just tell you. Tsunami can be modeled as a regular wave, but here the wavelength is very large. As I say, it is hundreds of kilometers. But what happens such waves, when they approaches towards the shoreline, the wave height increases. That part I didn't go here, but I'll just show you one of the thing here. I think I have a slide here. From there I'll say. That will give a clear idea how the C state is. Yeah, here you can see. See this wave that is coming from the deep sea, it's very regular. But when this wave is approaching towards the shoreline, what is happening? The amplitude is increasing. The depth is decreasing, the amplitude is increasing. And then what is happening in this zone? All the surf zone, what we call the surf zone, where the breaking is taking place. That makes the shoreline area very rough. In fact, the danger is always in the coastal area. It's not in the deep sea. Particularly So tsunami wave in the deep sea it is propagating is regular waves. It propagates in a regular, but when and modeling of tsunami waves are basically modeled as regular waves. In fact, as I said that it's here the wavelength is large, and that the large wavelength, the period. In fact, the speed of a tsunami wave it is similar to the like a speed of a jet flight, 700, 800 km/h, and its wavelength is 300 to 500 km. 300 to 500 km can be if it is around, as I said, 20 minutes if the 20 minutes is the period, the corresponding wave has 240 km is the wavelength. But they are based on all regular waves.
Thank you, sir. Another question, I have one doubt. Actually, you have discussed about linear wave theory, right?
Yes,
And
yes.
what about non-linear wave theories?
I have just talked about this one. In fact, this is the basically all the wave theory, what I told here. This is the linear part initially, but in fact, this is the detail about the nonlinear part. In fact, this equation, this is the governing equation. If this is a nonlinear boundary condition, this is also a nonlinear boundary condition. This together, if I combine this, this becomes this. I don't ignore this nonlinear part. If I don't ignore, for linear theory, I ignore this part by saying the quadratic terms does not contribute.
Yes, sir.
But if I keep this, then that becomes the nonlinear wave theory. But what we do to handle this problem, what we do, here we expand it, assuming z is equal, eta is very small, you take a Taylor series expansion about z is equal to 0. And then that will give you terms like this. Collect the coefficient of power, basically what I did in the perturbation, then I substitute eta, phi, and u in these nonlinear governing equations and collect the coefficient of epsilon, epsilon square and epsilon cube. This is becomes the first order theory, which is the linear theory. This is the quadratic part. This is the second order theory. This becomes the third order. But all, in general, this is the nonlinear wave theory. And coming back to the other part, this is the, as I say, that is the perturbational approach. But in general, one cannot solve this equation easily. Like people say, those who work on fluid mechanics, they say Navier-Stokes equation cannot be solved. In a similar, I say that even the linear, you have a potential Laplace equation, but the free surface condition is so complex, which I have shown you here, and that you cannot solve this. Yeah, this equation is so complex. You cannot solve this equation. Even if you have a Laplace equation as the governing equation, your boundary condition is this, then you cannot solve it. It's a highly nonlinear. So this is the nonlinear theory. And I have
in that case, we have to take in this case, we have to take some assumptions.
You have to somewhere linearize or take the higher different wave theory, yes. Or so that part by part you consider the first order, second order, third order, up to fifth, up to seventh order. People for engineering application, people have gone up to seventh order wave theory, depending on the application. Sir. And then I have given here the, I think I gave a chart here, how the first order wave theory and second order wave theory, what is the difference? You can see the first order, most simplest wave theory is the first order wave theory, linear theory. And you take the second order terms, include this much will be the variation. And then I have another picture here. Here it gives a clear picture. Shallow water, then transitional intermediate depth and deep water. You can see the linear theory. This part is the linear theory. Whereas second order wave theory, if I take, then I have a wider range. Then third order, if I have to include, I have another wider range, fourth order. And then altogether, you can say in this, all the wave theory comes in this fifth order and beyond that. So depending on what is your applicable area of application, whether your first order wave theory, in fact, in engineering practice, more than 80% of engineering activities is based on the linear wave theory, because we don't go and do some engineering activity where wave is rough, sea state is rough. We always create a calm zone. And first we create a calm zone, then we look at any port activity. Can you have any port activity when the water is rough? No. You have to build, you have to understand, you have to create the water. Like if the road is rough, you cannot drive properly. So same thing, if sea surface is rough, we cannot think of a ship which is moving or a boat is moving in the water body and at a speed of 100 kilometer or 120 kilometer. If the sea surface is rough, it will not able to, because wave it will kind of resistance it will provide. Like if a road is rough, you cannot drive smoothly. Similarly, if sea surface, so that is also for people who are working on ship design or ship motion problems. They always look at, always we have to see it. And as I say, deeper sea is more safe than the coastal area because water depth is changing, depth is changing, so its effect is will be appearing in the surface, though sea surface will be rough. Yeah, any more questions from students? Some questions will be asked.
Yeah, I could not find any questions from the student side. In fact, this is a new topic for them. I hope they will find it interesting. Thank you once again, sir, for this wonderful session. And now I invite Dr. Bhupesh Kumar Mahata, sir, for the vote of thanks.
On behalf of the department, thank you, sir. On behalf of Department of Mathematics, Amity Institute of Applied Sciences, I take the privilege of thanking our speaker, Professor Tilochan Sahu, sir, for sparing his spacious time for us, enlightening us about water wave and distribution of wave heights, which I am sure has provided new insight to our faculty members and students. My sincere thanks to our Honorable Founder President, Sir, Dr. Ashok K. Chauhan, Sir, Honorable Chancellor, Sir, Atul Chauhan, Sir, Honorable Pro Vice Chancellor, Sir, Dr. A.K. Srivastav, Sir, respected Dean Academic, Dr. A.K. Pandey, Sir, respected Directors, Dr. Vikas Misra, Sir, for their continuous support and guidance. I would like to express my gratitude to respected Registrar, Sir, Dr. P.K. Tripathi, Sir, Mr. P.K. Tripathi, Sir, IT and media team for their support. I would like to thank our HOI, Dr. Joyita Chattopadhyay, ma'am, and HOD, Dr. Biplav Bagh, sir, for their guidance and support. Without the audience, this event could not have been a success. I would like to thank to all the HOIs, HODs, esteemed colleague, faculty members, and my dear students for being here. Thank you all. Thank you.
Thank you.
Over to Smita, ma'am.
Thank you, sir. And we are thankful for this online session, and we wish and we are eagerly waiting for an offline session from you, and to be physically present over here in Amity University, Jharkhand. It will be a great privilege for all of us. If you can spare
Sure,
some time
sure.
someday to be here.
Yeah, sure. Sometimes in future we'll have it. Okay.
Thank you once again, sir,
Thank you.
for this your valuable time, and thank you all.
Thank you.